Okay, so in this video I want to talk a little bit more about the Black Scholes model, and I'm probably going to use a bunch of different pieces of paper as I move through. I thought that for some reason this would be more intuitive and easier to follow if I did this on a piece of paper. So hopefully I am correct, and I am just rewriting the equation here for Black Scholes model. Okay. The first thing that I want to say is let's think about this really intuitively. Okay, if the option is going to be used for sure, let's assume. Okay, so basically what I'm saying here is let's assume that D1 and D2 are very high. If D1 and D2 are very high, it means that ND1 and ND2 will be 100%, right? Basically, it's a normal standard distribution. So we have our normal distribution here. It's a standard normal distribution, so the mean is 1 and the standard deviation the mean is 0 and the standard deviation is 1. So if D1 and D2 are really far to the right here, right? D2 is always a little bit smaller than D1 here. But if we're really far to the right here, what it is saying basically is it's saying the option will for sure be in the money at expiration, or really close to be sure, because the probability is never going to be 100%, but it can be extremely close to 100%. So this is saying that our option, right, if D1 and D2 are really high, it's basically saying we will exercise the option anyway. So ND1 and ND2 will be 100%. In this case, the Black Scholes model is just telling us that the value of the option, the call premium, should just be this. And this should make sense if you understood what I told you earlier about continuous compounding. Okay, so let's think about an option that is really deep in the money. The strike price is, I don't know, 50 cents, and the underlying right now is valued at $200, right? If the option is for 3 months from now, the likelihood that the underlying's value go below 50 cents is extremely low. So D1 and D2 would be really high, and ND1 and ND2 would be close to 100%. In this case, you're basically just going to exercise the option no matter what. And if you exercise the option, you're going to get the underlying S. This is the value of the underlying today. Okay, but in order to get the underlying, you're going to have to pay the strike price, X. Okay, but there's a timing issue here. S is the value of the underlying right now. X is the strike price that you're going to have to pay at maturity of the option in T periods from now, T years from now. And so there's a timing issue between S and X. X is in the future, S is today. In finance, one of the basic principles is we can't compare amount of money at different point in time. So I'm going to need to find the PV for X. What is the value of X today, right? How much money would I need to invest today in the risk-free asset in order to be able to pay the strike price in the future? So X times e to the power of minus RT, this is just the PV. This is the PV of X, right? If you remember the equation for PV using continuous compounding, it was the FV times e to the power of minus RT. Well, X here is just our FV, and we're calculating a PV. Okay, so if the option is deep in the money, okay, well, the call premium should just be S, the value of the option today, minus the PV of our strike price. And that should make sense, right? Suppose that the underlying today is worth $100. So that's X. Suppose that the strike price is $1, right? We're going to use this option. It's pretty sure we're going to use this option. So this option should just be worth basically assuming the discount rate is 0%, right? If we assume the discount rate is 0% or the time to maturity is really short, close to zero, right? Well, then I should be willing to pay 99 bucks in order to buy this option. That should be my call premium because the option is worth literally $99 right now. This should be a minus. I don't know why I wrote a plus. Sorry about that. Okay. So hopefully this is clear, and hopefully this kind of explains what this does. Okay. Now the ND1 and the ND2 are a little bit confusing. Okay. The first thing that will confuse a lot of students is they're not the same numbers, right? But you can kind of think of both, and they're not exactly that. You shouldn't think of them like that exactly. We would have to talk a lot more about the math behind it in order to understand exactly what they are. But you can think of them a little bit as the probability of the option being in the money, right? What's the probability of being the option being in the money? Okay, and if you think about them that way, it kind of gives you that, okay, let's say 50% of the time my option will be in the money, and then I'll get X. But then 50% of the time, the option is in the money, so I'll lose X, the PV of X, right? Now, obviously, because D1 and D2 are not the same, these are actually not the probability of the option being in the money. Some people will teach you that at first, but it's actually not completely true, and it should be obvious, because if it was the option, the probability of the option being in the money, they should be both the same, right? So they're not, and the reasoning why is going a little bit beyond the pure view of this class. One thing though that I want to say is that D1, if we write D1, right? D1 was, and I'm doing it out of memory here, so I might have to look in a second, X plus, no, it's RT here, I believe. Where's my eraser? I'll look at it in a second. I'll pause the video after doing it, and I'll look at it in a second, but I'm pretty sure I can remember the equation pretty well. Okay, if I remember the equation correctly for D1, it was this. I'm just going to pause the video and go look. And I was correct. This is the equation for D1. Sorry, I don't know always these equations. I know them pretty close to by heart, but sometimes I make small mistakes in their value here. Okay, so if you look at D1 though, one thing that's interesting is I told you when we talked about the speculative premium that the closer the value of the underlying is to the strike price, right, the bigger the speculative premium is. And you can kind of see that here because we have S over X, right? When S is really far away from X, D1 will tend to, so S is much bigger than X, then D1 will tend to be bigger, right? When S is really close to X, okay, this number here, LX, so when these two numbers are really close to each other, S and X are the same, the underlying's value and the strike price are really close to each other, this ratio will be 1. And ln of 1 is just 0. If I put 1 in my calculator and then I calculate the ln of that, we get 0, right? So when these two are really close together, ND1 will tend to be closer to 50% because there's a 0 in here in the equation, right? And n of 0 is 50%. Obviously, there's other variables that enter here in the in D1. For example, R, the discount rate, right? And T, the time until maturity. If you go back and you look at my speculative premium, you'll see that R and T are also responsible for changing the speculative premium. Why? Well, because again, they show up in here. Okay. One more thing that I want to say here is you might have heard about the option delta before. Okay, the option delta is actually, and understanding this model and the Black Scholes model, if you've learned about all of the option Greeks, okay, delta is for the Greek letter delta, right? So option pricing has a lot of, we call it the options Greek, because they just have a whole bunch of different letters like delta that we refer to when we talk about option. Well, the option delta is actually just ND1. Okay, so if you follow options, or if you have worked, or like you're enjoying option and you try to trade options before, you might have heard people in videos or anything talk about the options delta. Well, the options delta is just this thing here. Okay, the options delta basically tells us that what is the increase in the price of the option, or the premium of the option, following a $1 increase in the price of the underlying. Okay, I could do more here. We could try to think about, okay, how does the option respond to changes in T, right? If T is bigger or shorter. I think I'm going to leave this out, because I think the math level for a lot of students will be maybe a little bit too low, and this is going to become a bit too complicated for most of you. But I hope that you can understand the basic idea behind this function, which is what I tried to do here. I hope you can try to understand that ND1 and ND2 are basically probabilities, right? And you can kind of, but not exactly, think of them as the probability that the option will be in the money. Okay, it's not exact. We would need more mathematics to understand everything better here. And then finally, I hope that you can remember what the option delta is. Okay, and I think that's all that I need you, or that I want you to remember for now. As I said, we could probably talk about how delta sigma s, time, so on and so forth, affect the price of the option, but I think that might be a little bit too difficult for some students, so I will leave this out. Thank you very much.